Hello friends, welcome back to my YouTube channel Journey with Vijay Kumar Shrivastav. Today we are going to study the topic biofortification. Before presentation, I would like to introduce myself. I am Vijay Kumar Shrivastav. I have done M.Sc Agriculture with a specialization in Agronomy from Pant University of Agriculture and Technology, Pantnagar in 1996 and presently associated with private job in seed industry. So let's proceed. First we will go through introduction of biofortification. The term biofortification came from Greek word bios means life and Latin word fortificare means make strong. Biofortification is the process of fortifying or increasing the nutritional quality of the foods through addition of micronutrients via agronomic practices, modern biotechnological practices or conventional plant breeding. Biofortification is a feasible and cost-effective method of providing micronutrient-rich diet to the families which cannot afford or has no access to balanced diet. Biofortification is similar with fortification in function as both of them increase the nutritional quality of the food. The major difference between them is that biofortification focuses on improving the nutritional content of the food during plant growth, while fortification is done manually during processing of the crops. In case of biofortification, instead of adding micronutrients in the harvested food, which is done in normal fortification, the plant's crops are themselves altered in biofortification so that they can produce nutrients on their own. Some examples of biofortification include iron biofortification of rice, zinc biofortification of wheat, amino acid and protein biofortification, etc. This method is also considered as a successful food-based approach to fulfill the gap of hidden hunger among the people of lower socio-economic groups who are facing micronutrient deficiencies. Therefore, so it is considered as a strategy to combat micronutrient deficiency. Biofortification is a great example of agriculture, health and nutrition sectors working in a combined way to produce better outcomes. Now details study about biofortification. Biofortification is the process of breeding nutrients into food crops which provides a comparatively cost-effective, sustainable and long-term means of delivering more micronutrients. Biofortification is the idea of breeding crops to increase their nutritional value. Biofortification differs from ordinary fortification because it focuses on making plant food more nutritious as the plant are growing, rather than having nutrients added to the food when they are being processed. This is an important improvement on ordinary fortification when it comes to providing nutrients for the rural poor who rarely have access to commercially fortified foods. As such, biofortification is seen as an upcoming strategy for dealing with deficiencies of micronutrients in low and middle income countries. In the case of iron, World Health Organization WHO estimated that biofortification could help curing the 2 billion people suffering from iron deficiency induced anemia. Biofortification aims to increase a select few nutrients in crops through plant breeding, whether using traditional techniques or through new tools of biotechnology. While there are 40 key nutrients that we must get from our food for good health, biofortified crop research is only focused on 3: zinc, iron and vitamin A. Biofortification is combined of high-yielding crop varieties with high nutrients crop varieties resulting in biofortified food crops. Now to study advantages of biofortification and how it is playing important role in reducing hidden hunger. Biofortified crops have higher chances to serve the poor people as biofortification is mainly done in staple crops like wheat, maize, sweet potato, etc., which is a major source of nutrients for the poorer households or families. Biofortification is highly cost-effective method as only one-time initial investment is needed to develop the fortified seeds or crops which fortify themselves later on. Also, there is no recurrent cost except some cost in maintenance breeding. It is sustainable method of fortification as fortification passes from one generation to next generation of crops without further investment and efforts as on biofortification. Biofortified crops have higher yielding along with higher disease resistance and drought tolerance, and this method is far more cheaper compared to addition of nutrients in the processed foods. Here to study importance of crop biofortification. It is very important to overcome the malnutrition in human beings. It is needed to increment of nutritional quality in daily diets. Biofortification is playing important role in improvement of plants or crop quality and increment of variability in germplasm. Biofortification for important crop plants through biotechnological applications is a cost-effective and sustainable solution for alleviating vitamin A deficiencies. There are some prerequisites which are needed for biofortification. Like plant breeders must be able to find a crop with high micronutrient content which can be bred into local varieties. Bioavailability of the crops must be ensured. Nutritional effectiveness of biofortified crops must be established. Both farmers and food consumers must have full acceptance towards this new food-based approach and make a part of their regular diet. Now to go through research work on biofortification. Research is currently underway to develop biofortified crops like rice, wheat, sorghum, banana, lentil, potato, sweet potato, cassava, beans and maize crops in Africa, Asia and Latin America. Part of this research is managed by the Consultative Group on International Agriculture Research, divided across 3 units. First one, the International Rice Research Institute, focusing on genetically modified GM rice. Second, the International Potato Center, focusing on sweet potato. And third, the harvestplus program, which coordinates all the rest. The funding comes from the Bill and Melinda Gates Foundation and USAID, among others. Private research firms are also dedicated for the service to the biofortification project by the PepsiCo, DuPont, Bayer, Nestle and others. About 2 billion people around the world suffer from micronutrient deficiencies, also known as hidden hunger. This lack of critical vitamins and minerals can have long-term, irreversible health effects that affect well-being and long-term development prospects. Modern plant breeding has been historically oriented towards achieving high agronomic yields rather than nutritional quality, and other efforts related to alleviating the problem have been primarily through industrial fortification or pharmaceutical supplementation. Micronutrient malnutrition or the hidden hunger is very common among women and preschool children, caused mainly by low dietary intake of micronutrients, especially zinc and iron. Biofortification, the process of increasing the bioavailable concentrations of essential elements in edible portions of crop plants through agronomic intervention or genetic selection, may be the solution to malnutrition or hidden hunger mitigation. The consultative group on international agriculture research has been investigating the genetic potential to increase bioavailable iron and zinc in staple food crops such as rice, wheat, maize, common beans, and cassava crops. Now, biofortification strategies. The biofortification strategy seeks to put the micronutrient dense traits in those varieties that already have preferred agronomic and consumption traits such as high yield. Marketed surpluses of these crops may make their way into retail outlets, reaching consumers in first rural and then urban areas, in contrast to complementary interventions such as fortification and supplementation that begin in urban centers. Biofortified staple foods cannot deliver as high a level of minerals and vitamins per day as supplements or industrially fortified foods, but they can help by increasing the daily adequacy of micronutrients intakes among individuals through the life cycle. As per Boyce et al. In 2011, and there are various minerals and vitamins which are working for biofortification in food crops like iodine, vitamin A, iron, zinc, calcium, selenium, and folate. Biofortification is a technique that uses conventional breeding methods to produce more nutritious crops with a high contents of vitamin A, zinc, iron, or other micronutrients than standard crop varieties. Biofortified crops already contributing to healthier diets in Asia and Africa, which includes vitamin A sweet potatoes, zinc rice, and iron beans. ICAR's harvestplus program leads this work related to biofortification. ICAR's biofortification research is closely aligned with the Sustainable Development Goals, and there are various crops under which biofortification is working well, like cassava, maize, sweet potato, beans, pearl millet, rice, and wheat crops. Conventional interventions have a limited impact, so biofortification has been proposed as an alternative long-term approach for improving mineral nutrition. As per Joe et al. 2007, biofortification focuses on enhancing the mineral nutritional qualities of crops at source, which encompasses processes that increase both mineral levels and their bioavailability in the edible part of staple crops. Biofortification is also likely to be more accessible than conventional interventions in the long term because it removes hurdles such as the reliance on infrastructure and compliance. Moreover, plant assimilates minerals into organic forms that are naturally bioavailable and contribute to the natural taste and texture of the food. Economic studies have shown many potential health benefits of biofortification strategies, especially in combination with conventional strategies. There are two methods of biofortification. First one is selective breeding and second is genetic engineering. Genetic engineering and selective plant breedings is resulting to biofortification by improving the nutritional quality of the food, and there are some agronomic approaches by which we can add the nutritious crop varieties through mineral fertilizer, foliar fertilization, plant growth promoting microorganisms. Through agronomic biofortification, it can be done through soil application, foliar application, and seed treatments, while in case of genetic biofortification, it is done by conventional breeding and transgenic approaches. Here we have shown the picture for the comparison of traditional fortification and biofortification. In case of traditional fortification, the crop grain yields are added with nutrients, while the food processing, Because of this, the cereals are available with added nutrients for the consumption. By utilizing, more nutrients are consumed by the customers, which is increasing the nutrient level in the body as per the requirements. While in case of biofortification, there are two methods used: selective breeding or genetic modifications. In this method, the plants producing low levels of nutrients are converted to the high level of nutrients through breeding and selective approaches. And by the utilization of such nutritious crop, there is more consumption of nutrients after intake. So these are the difference where in case of traditionally we are adding while food processing, and in case of biofortification through breeding method, the crop is getting to be altered in its nutritious levels. First method of biofortification is selective breeding method. Using this method, plant breeders search seed or germplasm banks for existing varieties of crops which are naturally high in nutrients. They can often crossbreed these high nutrients varieties with high yielding varieties of crops to provide a seed with high yields and increased nutritional value. Under this method, crops must be bred with sufficient amount of nutrients to have a measurable positive impact on human health. As such, they must be developed with the involvement of nutritionists who study whether the consumers of the improved crop can absorb the extra nutrients and the extent of which storage, processing, and cooking of the crops affect their available nutrient levels. Bred wheat with high grain iron and zinc has been developed through radiation breeding, and this selective breeding method is prevalent at present as it is less controversial than genetically engineering crops. Second method of biofortification is genetic engineering method. Genetic engineering assesses genes from any source and introduces them directly into the crop. Plant breeding is limited to genes that can be sourced from sexually compatible plants, whereas genetic engineering has no taxonomic constraints and even artificial genes can be used. The main advantage of genetic engineering and plant breeding approaches for mineral enhancement is that investment is only required at the research and development stage, and thereafter the nutritionally enhanced crop are entirely sustainable. Golden rice is an example of GM crop developed for its nutritional value. The latest version of golden rice contains genes from a common soil bacterium Erwinia and maize and contains increased level of beta carotene, which can be converted by the body into vitamin A. Golden rice is being developed as a potential new way to address vitamin A deficiency. Seed priming is other process which is followed for improving the nutritional quality. Nutrient seed priming significantly increased seed contents of primed nutrients. In nutrient solution lacking zinc and manganese, growth of maize plants primed with zinc plus manganese increased by more than 50% and 100% respectively as compared to control treatment. According to one report, it is possible to prime seeds before sowing by bombarding them with iron oxide nanoparticles. This method would trigger more iron acquisition in the wheat plants and thus increase the nutritive value of the grains. Now to study the status of biofortification. In recent years, several crops with increased micronutrient concentration have been introduced in several developing countries, and this has helped in overcoming nutrient deficiency in the target population. For example, the introduction of the orange sweet potato biofortified with beta carotene increased vitamin A intake among children and women in Mozambique and Uganda, and maize biofortified with provitamin A increased the concentration of vitamin A in 5 to 7-year-old children in Zambia who consumed it for 3 months. Similarly, serum ferritin and total body iron were improved in iron deficient adolescent boys and girls from Maharashtra, India who consumed iron biofortified pearl millet flatbread for 4 months. Regarding pulse crops, the consumption of iron biofortified beans for 4.5 months improved the hemoglobin and total body iron in iron depleted University Oman in Rwanda. By the end of 2016, more than 150 biofortified varieties of 10 crops had been released in 30 countries, and these are consumed by more than 20 million people in developing countries. harvestplus, which is a major NGO in the development of biofortified crops, primarily use conventional breeding techniques and have not yet spent more than 15% of their research budget on genetically modified crops when conventional methods failed to meet nutritional requirements. To date, harvestplus has released or tested more than 290 varieties of 12 staple food crops, including vitamin A orange sweet potato, iron beans, iron pearl millet, vitamin A yellow cassava, vitamin A orange maize, zinc rice, and zinc wheat in 60 countries. Iron beans are delivered in Rwanda and Democratic Republic of Congo, zinc rice is in Bangladesh, and zinc wheat is in India and Pakistan. As earlier we discussed, harvestplus is focusing on biofortification for enhancement of nutritional varieties. They have targeted countries and targeted crops like maize for vitamin A project in Zambia, then sweet potato for enhancement of vitamin A in Uganda, cassava crops for vitamin A working in Nigeria, pearl millet for increasing the nutritional value of iron in India, wheat zinc for India and Pakistan countries, rice crop for enhancing the zinc content which is working for India and Bangladesh countries. After that, beans crops to enhance the iron content. The project is in Rwanda and DRC countries. Now here we will study about significance of biofortification. First, to study in low and middle income countries where biofortification plays very important role for increasing the nutritional value of the crops. Deficiencies of various micronutrients including vitamin A, zinc, iron are common in low and middle income countries and affect billions of people. This can lead to, amongst other symptoms, a higher incidence of blindness, a weaker immune system, a stunted growth, and impaired cognitive development. The poor, particularly the rural poor, tend to subsist on a diet of staple crops such as rice, wheat, and maize, which are low in these micronutrients, and most cannot afford efficiently cultivate enough fruits, vegetables, or meat products that are necessary to obtain healthy levels of these nutrients. As such, increasing the micronutrient levels in staple crops can help prevent and reduce the micronutrient deficiencies. In one trial in Mozambique, eating sweet potatoes biofortified with beta-carotene reduced the incidence of vitamin A deficiency in children by 24%. This approach may have advantages over other health interventions such as providing food fortified after processing or providing supplements. Biofortification is also fairly cost effective after an initial large research investment where seeds can be distributed. The implementation costs are nil or negligible as opposed to supplementation, which is comparatively expensive and requires continued financing over time, which may be jeopardized by fluctuating political interest. Research on this biofortification project approach is being undertaken internationally with major efforts ongoing in Brazil, China and India. Now, biofortification in high-income countries, like poor countries, it is also taking place the activities of biofortification in high-income countries. Researchers at the University of Warwick have been looking for ways to boost the low selenium levels in British grains and have been working to help to develop a grain to be used in making bread biofortified with selenium. Here we have shown the differentiation between fortified versus biofortified crops. In case of fortified, the crop product is added with mineral nutrients while processing, by which the nutrients are added during processing and it is consumed by the customers to meet the nutritional requirements. While in case of biofortified, the nutrients are added in the crop genetics and which is forever and it will produce the nutrients for the nutritional requirement on itself. There are some challenges in biofortification, like initial cost of research may be higher for developing and underdeveloped countries. There may be difficulty in maintaining regulatory compliance as extremely precautionary regulations must be followed, and fewer profit margins in the production and distribution of crops make it less attractive for private sectors. Thus, a scarcity of government funds may worsen the scenario for the public. So this presentation was all about biofortification. Hope this will be useful to all of you. I have given here my YouTube channel details, Journey with Vijay Kumar Shrivastav. Having request, please visit the channel, subscribe it and provide your kind and valuable feedback for further improvements. Thank you.